Hello, friend. Welcome back to another quiet journey through the cosmos. Tonight, the sky feels different. Wider, maybe. Deeper than it should be. There's a light up there, steady and ancient, that left its star long before you were born. Before your grandparents were born. Before humans learned to write, or dream, or wonder. And tonight, that light finally reaches your eyes. But here's what makes you pause. What makes the night feel strange. That star, the one whose light you're seeing right now, might already be gone. Died centuries ago in a flash so bright it could have outshone an entire galaxy. And you're only just now seeing its last breath. Some nights when you look up, you're not seeing the universe as it is. You're seeing its memory. You're seeing light from stars that might no longer exist, traveling across an ocean of darkness so vast that by the time it reaches you, everything has changed. The universe doesn't update in real time. It whispers to us in echoes. Before we drift further into this quiet mystery, I want to thank you for being here. If you find comfort in these journeys through space and science, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for listening. Now, let's begin. Tonight we are going to explore something both beautiful and violent, something that creates and destroys in the same breath. We're going to talk about supernovae, the death of stars, and the quiet power they hold over everything you see, everything you touch, even everything you are. Because here's the truth, scientists have slowly uncovered you exist because stars died. The calcium in your bones, the iron in your blood, the carbon that makes up every cell in your body, none of it existed until a star exploded and scattered its insides across the cosmos. You are made of stardust, yes, but more precisely, you are made of dead stardust. You are the aftermath of violence turned into life. Most people think of stars as eternal, as fixed points of light that will always be there. Ancient sailors used them for navigation. Poets used them as symbols of constancy. Lovers made wishes upon them. For thousands of years, humans believed the heavens were unchanging, perfect, divine. Then, on November 11th, 1572, a Danish astronomer named Tycho Brahe looked up and saw something impossible. A new star had appeared in the constellation Cassiopeia, blazing so brightly it could be seen in broad daylight. It was brighter than Venus, brighter than anything except the sun and moon. For months it dominated the night sky, then slowly faded and eventually vanished. Tycho wrote a book about it, carefully titled De Nova Stella, about the new star. But it wasn't new at all. It was old. It was a star in the final catastrophic moment of its death. It was a supernova. What Tycho didn't know, what no one could have known at the time, was that he was watching an event that had already happened 6,000 years earlier. The star that exploded was 6,000 light years away, meaning its light took 6,000 years to cross the void and reach Earth. By the time Tycho saw it shine, the explosion itself was ancient history. The star was already gone, replaced by an expanding cloud of gas, still racing outward, still carrying the elements forged in that final moment. Even now, more than 450 years after Tycho observed it, that cloud is still spreading, still glowing faintly, a ghost in the sky that telescopes can still detect. Scientists call it SN 1572 Tycho's supernova, and it changed everything. It shattered the idea that the heavens were perfect and unchanging. It proved that stars could die. And here's what makes supernovae so strange, so hard to fully grasp. They are both an ending and a beginning. A star dies, but in dying, it gives birth to nearly everything. Before supernovae, the universe was simple. After the Big Bang, there was only hydrogen and helium, the two lightest elements drifting in clouds across the darkness. That's it. No carbon, no oxygen, no nitrogen, no metals. No planets, no life, no possibility of you. The universe was sterile. But then the first stars formed massive and short-lived, and they began to cook heavier elements in their cores through fusion, smashing atoms together under unimaginable heat and pressure. Slowly, over millions of years, they built up layers heavier and heavier until their cores were made of iron, and iron was the end. Iron can't be fused to release energy. Iron is the ash of fusion, the point where a star's nuclear fire stops feeding itself. And when that happens, when the core becomes iron, the star's time is up. For a star, this is the moment of collapse. Gravity, which has been held at bay for millions of years by the outward pressure of fusion, suddenly wins. The core collapses inward in less than a second, compressing to unimaginable densities. And then, in a rebound shockwave of staggering power, the star explodes. This is a supernova. In that single moment, the star releases more energy than it produced during its entire lifetime. For a few weeks, it shines with the brightness of 100 billion suns. From across the universe, that single dying star can briefly outshine an entire galaxy. But here's the miraculous part. The part that connects this cosmic violence to you, sitting here tonight in that explosion. In the intense heat and pressure of the shockwave, the star forges new elements heavier than iron elements that couldn't be made any other way. Gold, silver, platinum, uranium, all the elements that make planets solid, that make oceans salty, that make life complex. They are born in those few seconds of cataclysm. The explosion scatters them into space where they mix with clouds of gas and dust, and eventually, billions of years later, they collapse into new stars, new planets, new chances for life. Our sun is a second or third generation star made from the remnants of stars that died long before the solar system existed. The Earth beneath your feet is built from their ashes. Scientists have calculated that a supernova within our galaxy happens on average once or twice per century. That might sound rare, but across the entire observable universe with its 2 trillion galaxies, there are roughly 10 supernovae exploding every single second. Right now, as you listen to this, somewhere in the universe, a star is dying. Its core is collapsing. Its outer layers are being hurled into space at 10% the speed of light. Elements are being forged. And the light from that explosion is beginning its long journey across the cosmos, traveling for millions or billions of years, until one night, far in the future, someone will look up and see a new star in their sky. We live in a universe shaped by death. The atoms in your hand, the oxygen you're breathing, the light, you see all of it traces back to stars that burned and burst and gave themselves to the void. Supernovae are not just explosions, they are acts of creation. They are the universe's way of turning simple into complex, of turning nothing into everything. Without them, there would be no planets, no chemistry, no biology, no thought, no wonder, no you. And here's something even stranger, something that scientists only realized in the 20th century. When you look at a distant supernova through a telescope, you're not just seeing light, you're seeing time itself behave differently. Because of the immense gravity near the collapsing core, time slows down just as Einstein predicted. To an outside observer, the explosion seems to unfold in slow motion. The star appears to brighten over weeks, but from the perspective of the star itself, the collapse happens almost instantaneously. Time, like everything else, bends under the weight of dying stars. So, tonight when you think about the stars above, you don't think of them as eternal. Think of them as temporary, as fragile as waiting. Some of them are already dead, their light still traveling toward us, carrying the memory of their last moments. Others are still burning, fusing hydrogen into helium, quietly holding themselves together against the pull of gravity. And a few, the massive ones, the ones 10 or 20 or 50 times heavier than our sun, are nearing the end. Their cores are filling with iron. Their time is running out. One day, maybe tomorrow, maybe 1,000 years from now, they will collapse, explode, and send their light racing across the universe. And when that light finally reaches Earth, someone will look up and see what Tycho saw, a new star where there was none before. But it won't be new. It will be the oldest story in the cosmos told again. You don't need to understand all of this tonight. You don't need to hold every detail. Just rest in the knowledge that you are connected to something vast, something ancient, something still unfolding. The stars above you are not separate from you. They are your ancestors in a way more literal than any family tree. You exist because they died, and their light traveling for eons is still reaching you, now still telling you their story. But how does it happen exactly? How does a star that has burned steadily for millions of years suddenly tear itself apart in a fraction of a second? What breaks the balance? What tips a star from life into death? To understand that, we need to look inside a dying star, into its layers, its core, the place where gravity and pressure and heat are locked in a battle that for a while holds everything together, until it doesn't. Inside every star there is a war. It's silent and visible, and it has been raging since the star was born. On one side, gravity pulling inward with relentless force, trying to crush everything into a single point. On the other side, heat and pressure from nuclear fusion, pushing outward, resisting collapse. For millions, sometimes billions of years, these two forces balance perfectly. The star holds its shape. It burns steadily. But this balance is not eternal. It's a countdown. And when the fuel runs out, gravity wins. To understand how a star explodes, you first need to understand how it lives. And the architecture of a massive star, the kind that will one day become a supernova, is more complex than most people imagine. It's not just a ball of burning gas. It's a layered structure like an onion, with each layer fusing different elements, each one hotter and denser than the last. At the surface, the star looks calm, almost serene. But deep inside in the core, the temperature is millions of degrees, and atoms are being smashed together with such force that they fuse into heavier elements, releasing the energy that keeps the star alive. Let's walk through these layers, starting from the outside and moving inward. Imagine you could slice a massive star open and look inside. At the outermost layer, you'd find hydrogen, the simplest and most abundant element in the universe. This is where the star began its life, fusing hydrogen into helium in its core. For most stars, this phase lasts the longest. Our Sun, for example, has been fusing hydrogen for about 4.6 billion years, and it will continue for another 5 billion. But a star much larger than the Sun, say 20 or 30 times more massive, burns through its hydrogen in just a few million years. The more massive the star, the hotter its core, and the faster it consumes its fuel. It's a paradox. The biggest stars live the shortest lives. Once the hydrogen in the core is exhausted, the core contracts. It gets hotter. And when it reaches about 100 million degrees Kelvin, a new reaction begins. Helium atoms start fusing together, creating carbon and oxygen. This is the second layer, the helium-burning shell. The star has entered a new phase of its life. It's no longer a main sequence star. It's become a red giant, or if massive enough, a red supergiant. Its outer layers expand dramatically, sometimes swelling to sizes larger than Earth's orbit. If our Sun went through this phase while the solar system still existed, it would engulf Mercury, Venus, and possibly Earth. But at the core, things are getting tighter, denser, hotter. Then the helium runs out. The core contracts again. Temperature rises. At around 600 million degrees, carbon begins to fuse, producing neon and magnesium. Now, there are 3 layers, 3 shells of fusion happening simultaneously, each one surrounding a hotter, denser core. The star is like a furnace with multiple fires burning at different temperatures, each one feeding off the ashes of the one before it. This process continues layer after layer, element after element. Neon fuses into oxygen. Oxygen fuses into silicon. Each stage lasts shorter than the last. Carbon burning might last a few thousand years. Neon burning just a few years. Oxygen burning mere months. Silicon burning, which is the final stage before catastrophe, lasts only a few days. And then, at the very center, at the heart of the star, something terrible forms. Iron. Iron nuclei are the most stable configuration of protons and neutrons in nature. Fusing iron requires energy instead of releasing it. Iron is the ash that cannot burn. It accumulates in the core, growing heavier with every passing hour, and the star, for the first time in its life, can no longer generate the pressure needed to hold itself up. Gravity has been waiting for this moment. The instant the core becomes predominantly iron, the balance breaks. The core collapses. This is the architecture of a dying star. 6 concentric shells, each burning a different element, each one representing a stage in the star's slow march toward death. Hydrogen on the outside, then helium, carbon, neon, oxygen, silicon, and finally at the center, iron. It's a structure built by fusion layer by layer over millions of years, but it's also a time bomb. Because once that iron core forms, the clock is no longer measured in millions of years or even thousands. It's measured in seconds. Scientists didn't always know this. For most of human history, stars were mysterious, unreachable, divine. Even in the early 20th century, when physicists first began to understand nuclear fusion, the internal structure of stars remained theoretical, built on equations and guesses. Then in the 1930s, an Indian astrophysicist named Subramanian Chandrasekhar made a discovery that would change everything. He calculated that there was a limit to how massive a star's core could be before gravity overwhelmed all other forces. That limit, now called the Chandrasekhar limit, is about 1/4 times the mass of our Sun. Any core more massive than that, and gravity becomes unstoppable. The core will collapse into either a neutron star or a black hole. Any core less massive, and the star can die more gently, shedding its outer layers and leaving behind a white dwarf, a dense ember, slowly cooling over billions of years. Chandrasekhar calculated this while sailing from India to England in 1930 at the age of 19. He presented his findings to the scientific community, expecting praise. Instead, he was met with skepticism, even ridicule, particularly from the famous astronomer Arthur Eddington, who refused to believe that stars could collapse so catastrophically. It took decades for Chandrasekhar's work to be fully accepted. He eventually won the Nobel Prize in 1983, more than 50 years after his initial discovery. But his equations were correct. They described the fate of every massive star. They predicted supernovae. What Chandrasekhar showed was that a star's death is not random. It's determined by physics, by the interplay of gravity, pressure, and nuclear forces. Once a core exceeds 1.4 solar masses and runs out of fuel, nothing can stop the collapse. No force in nature, except perhaps the strange quantum pressure that forms neutron stars, can resist it. The core implodes, and the outer layers, no longer supported, fall inward at speeds approaching a significant fraction of the speed of light. In less than a second, the core compresses from something the size of Earth to something the size of a city. Density increases 1 trillion-fold, and then, like a rubber ball bouncing off a wall, the infalling matter rebounds. A shock wave rips outward, tearing through the star's layers, and the star explodes. But here's the part that surprises most people: the explosion itself, the light. We see the brilliant supernova that can outshine a galaxy that's not the moment of collapse. The collapse happens first in darkness, in silence. The light comes later, when the shock wave reaches the surface of the star and blasts the outer layers into space. There's a delay, sometimes hours, between the core collapse and the visible explosion. During that time, the star is already dead at its center, but its surface doesn't know it yet. Light from the core takes time to travel outward through the dense layers. The star dies from the inside out. And here's another detail, one that connects back to the layers we talked about earlier. When the shock wave passes through those shells of different elements, it heats them, compresses them, and triggers even more fusion. Elements that couldn't form in the calm burning of the star's life are suddenly created in the chaos of its death. The intense heat and pressure in the supernova's shockwave allow nuclei to capture neutrons rapidly, a process scientists call the R process, or rapid neutron capture. This is how the heaviest elements in the universe are made. Gold, platinum, uranium, thorium, all the elements heavier than iron, they don't come from the steady burning of stars. They come from the violence of their deaths. In a way, a supernova is the universe's alchemy lab. For centuries, alchemists tried to turn lead into gold, believing it was possible through secret formulas and mystical processes. They failed, of course. But they weren't entirely wrong. Gold can be made from lighter elements. It just requires the energy of an exploding star. Every gold ring, every piece of jewelry, every fleck of gold ever mined from the Earth, it was forged in a supernova billions of years ago, then scattered into space, eventually coalescing into the dust cloud that became our solar system. You're wearing the remnants of stellar death on your finger, the architecture of a star. These layers of fusion, this gradual buildup from hydrogen to iron, it's not just a structure, it's a story. It's the story of how the universe builds complexity, how it takes the simplest elements and through heat and pressure and time, transforms them into everything. Each layer represents a chapter in that story. Hydrogen, the beginning, the raw material of the cosmos. Helium, the first transformation, proof that fusion works. Carbon, the foundation of life. Oxygen, the breath we take. Silicon, the basis of rock and sand. And iron, the end, the element that cannot give any more. Iron is the star's limit, the point where chemistry stops and gravity takes over. There's a certain poetry in this, a rhythm. The star builds layer by layer, reaching for complexity, and then when it can go no further, it gives everything away. It collapses, explodes, and scatters those layers across light years of space. The hydrogen, the helium, the carbon, the oxygen, all of it mixing together, cooling, eventually forming new stars, new planets, new chances. The universe recycles itself. Nothing is truly lost. Death in the cosmos is just transformation. Scientists now use computer simulations to model these layers, to watch in virtual time how a star evolves from birth to death. They input the star's mass, its composition, its rotation, and the simulation runs forward, compressing millions of years into minutes. You can watch the core heat up, watch the layers form, watch the iron accumulate. And then in the final frames of the simulation, you see the collapse. The core shrinks in an instant, the shockwave forms, and the star tears itself apart. These simulations match what we observe in real supernovae. They confirm Chandrasekhar's math. They show us that we understand, at least in broad strokes, how stars die. But understanding the architecture doesn't make it any less astonishing. A star holds itself together for millions of years through a delicate balance, and then in a fraction of a second, that balance is destroyed. The forces involved are almost beyond comprehension. The gravitational pull at the center of a collapsing core is so intense that space itself warps, that time slows, that matter is compressed into states that don't exist anywhere else in the universe. And all of this happens because a star ran out of fuel, because it reached iron and could go no further, because gravity, patient and relentless, finally won. So, when you think of a star, don't just think of light. Think of layers. Think of a battle being fought deep inside a battle, that the star is slowly losing one element at a time. Think of the iron core growing silent and deadly at the heart of something that looks from the outside perfectly calm. Because that's what a massive star is in its final days. It's a structure holding itself together against impossible odds, knowing in some abstract physical sense that collapse is inevitable. The only question is when. And when the moment comes, when the core finally gives way, the transformation is instant. The star that took millions of years to build is destroyed in less time than it takes you to blink. But what does that moment feel like if a star could feel? What happens in that first fraction of a second when the core begins to fall inward, when gravity takes over and nothing can stop it? That's where we're going next, into the collapse itself. Into the moment when a star realizes it can no longer hold its own weight and everything changes. There is a moment just before everything ends when the star knows. Not consciously, of course, but physically, mathematically, inevitably. The iron core has grown too heavy. Fusion has stopped. And for the first time in millions of years, there is nothing pushing back against gravity. In that instant, the core begins to fall, not slowly, not gradually, but catastrophically. The collapse happens so fast that if you could watch it in real time, you would miss it. 1/4 of a second. That's all it takes for a core the size of Earth to compress into something smaller than Manhattan. 1/4 of a second to change everything. Imagine trying to crush a car into the size of a marble. Now, imagine doing that to an entire planet. That's what happens during core collapse. The density increases so rapidly that the laws of physics you learned in school start to bend. Matter behaves in ways that shouldn't be possible. Electrons, which normally orbit atomic nuclei at comfortable distances, are forced into the nuclei themselves, merging with protons to form neutrons. The star's core is no longer made of atoms. It's made of neutrons packed so tightly together that a single teaspoon of this material would weigh as much as Mount Everest. And the temperature, already millions of degrees during the star's life, now spikes to over 100 billion degrees Kelvin. That's hotter than the core of any living star, hotter than the surface of any supernova. For a brief moment, the collapsing core becomes the hottest place in the universe. But here's the strangest part. The part that scientists didn't predict until they actually observed it. Most of the energy from the collapse doesn't come out as light. It comes out as neutrinos. Neutrinos are ghost particles, nearly massless, almost impossible to detect. They pass through normal matter as if it isn't there. Right now, billions of neutrinos from the sun are passing through your body every second, and you don't feel a thing. They fly through the earth, through the oceans, through solid rock without interacting. But during a supernova, so many neutrinos are produced, and the core is so dense that even neutrinos struggle to escape. They carry away 99% of the collapse's energy. Only 1% goes into the explosion itself, into the light and shock wave that we see. Think about that. The brightest event in the universe, an explosion that can outshine 100 billion stars, is powered by just 1% of the total energy released. The other 99% simply vanishes into space, invisible, undetectable, except by the most sensitive instruments humans have ever built. We know this because of one supernova in particular, SN 1987A. It exploded on February 23, 1987 in the Large Magellanic Cloud, a small galaxy orbiting our own Milky Way about 168,000 light-years away. That means the light we saw in 1987 had been traveling for 168,000 years. The star that exploded, a blue supergiant called Sanduleak, 69°202, died long before humans existed, long before Homo sapiens walked the Earth. But its light arrived in 1987, and astronomers were ready. For the first time in history, we had neutrino detectors. 2 of them, one in Japan called Kamiokande, and one in the United States called IMB, the Irvine, Michigan Brookhaven detector, both buried deep underground to shield them from cosmic rays. On the morning of February 23rd, just before the light from SN 1987A reached Earth, both detectors registered a burst of neutrinos, 19 neutrinos in total, arriving over a span of about 13 seconds. That might not sound like much, but consider this. Detecting even a single neutrino is extraordinarily difficult. 19 neutrinos in 13 seconds was a flood and unmistakable signal. And they arrived 3 hours before the light did. 3 hours. Because neutrinos traveling at nearly the speed of light escaped the star's core immediately when it collapsed. The light, on the other hand, had to fight its way out through the dense outer layers of the star, a journey that took hours. By the time the light reached the surface and the supernova became visible, the neutrinos were already long gone, racing through space, occasionally interacting with a water molecule deep underground in Japan or Ohio. This was proof that core collapse happens, that neutrinos carry away most of the energy, that our understanding of supernova physics, built on decades of theory and mathematics, was correct. Scientists around the world celebrated. SN 1987A became the most studied supernova in history. and it's still being observed today. Telescopes watch the expanding debris, tracking how the shock wave interacts with surrounding gas, how elements mix and cool and form dust. Every year we learn something new from it. But the most important lesson came in those first few hours when neutrinos arrived before light and we realized we had witnessed the collapse itself, not just the aftermath. Now, let's talk about what happens inside that collapsing core, because the physics here is almost unimaginable. As the core compresses, the density rises so high that the neutrons themselves begin to resist. There's a quantum mechanical effect called neutron degeneracy pressure, a consequence of the Pauli exclusion principle, which states that no two fermions can occupy the same quantum state. Neutrons are fermions. When you squeeze them together, they push back not because of heat or motion, but because of the fundamental rules of quantum mechanics. For a core just slightly more massive than the Chandrasekhar limit, neutron degeneracy pressure is strong enough to stop the collapse. The core rebounds and the infalling outer layers smash into this suddenly rigid surface. The result is a shock wave, a wall of pressure and heat, traveling outward at thousands of kilometers per second, tearing through the star's layers and eventually exploding the star apart. What's left behind is a neutron star, a sphere maybe 20 kilometers across, spinning rapidly, emitting beams of radiation, like a cosmic lighthouse. But if the core is too massive, even neutron degeneracy pressure isn't enough. Gravity overwhelms everything. The core doesn't stop collapsing. It keeps shrinking past the neutron star stage, past any known form of matter, until it crosses a boundary called the event horizon. At that point, the core becomes a black hole. No light can escape. No information can escape. The star has collapsed into a singularity, a point of infinite density, or at least what our equations predict as infinite density. In truth, we don't know what happens at the center of a black hole. General relativity breaks down. Quantum mechanics offers no clear answers. It's one of the great unsolved mysteries in physics. But from the outside, from the perspective of the universe, the result is clear. The star is gone, replaced by a region of space-time, so warped that nothing, not even light, can climb back out. Scientists estimate that roughly half of all supernovae leave behind neutron stars, and the other half leave behind black holes. It depends on the mass of the core at the moment of collapse. A core between about 1.4 and 3 solar masses becomes a neutron star. Anything heavier becomes a black hole. But here's the catch: we can't always tell which outcome will occur just by looking at the star before it explodes. Two stars of similar mass might collapse differently, depending on how much mass they lose during their lifetimes, how fast they rotate, and how their cores are structured. It's not a simple equation. The universe has room for variation, for surprise. There's another detail worth mentioning, one that took decades to understand: the shock wave that explodes. The star doesn't start immediately. When the core collapses and rebounds, the initial shock wave forms, but it stalls. It loses energy as it pushes through the dense layers above the core, heating the material, dissociating iron nuclei, fighting against gravity. For years, computer simulations showed the shock wave stalling and fading, unable to reach the star's surface. This was a problem. Supernovae clearly happen. We observed them, but the simulations couldn't reproduce them. Something was missing. Then scientists realized that neutrinos, those ghost particles escaping the core by the trillions, might be the key. A small fraction of them, less than 1%, interact with the stalled shock wave, depositing energy, reviving it. It's called neutrino-driven convection, and it's one of the most complex processes in astrophysics, involving turbulence, radiation, and quantum interactions, all happening simultaneously. Even today, with the most powerful supercomputers in the world, scientists struggle to fully simulate it. But the basic idea is clear. Without neutrinos, stars might not explode at all. They might just collapse into black holes quietly, invisibly. without ever producing a supernova. Neutrinos. The particles that pass through everything are the reason we see supernova at all. And here's something that might surprise you. The collapse itself makes almost no sound. In space, of course, there is no air, no medium for sound waves to travel through, so everything is silent. But even if you could somehow be inside the star suspended in the collapsing layers, you wouldn't hear the collapse as a sound. You might feel it, a sudden pressure wave, a shift in the forces around you, but not a sound in the way we understand it. The shock wave, when it forms, travels faster than the speed of sound in the star's material, so it arrives before any acoustic signal could. It's a supersonic explosion, a silent catastrophe. The violence of the collapse is expressed not in noise, but in light and neutrinos, in gravitational waves rippling through the fabric of space-time itself. Gravitational waves. We need to talk about those. When the core collapses asymmetrically, when it wobbles or rotates or fragments unevenly, it creates ripples and space-time distortions that propagate outward at the speed of light. These are gravitational waves predicted by Einstein in 1915, but not directly detected until 2015 by the LIGO Observatory. Supernovae are thought to produce gravitational waves, especially if the core collapses in a lopsided way, but so far we haven't detected them from a supernova. The signal is too weak, the distance too great. LIGO is sensitive enough to detect gravitational waves from colliding black holes billions of light years away. But a supernova in our galaxy would be much closer and much easier to detect. Scientists are waiting. If a supernova happens in the Milky Way within the next few decades, and if our detectors are running, we will measure gravitational waves from the collapse itself. We will feel the fabric of space trembling as a star dies. That data would be invaluable, a way to peer inside the collapse to see how matter behaves under conditions we can never recreate in a laboratory. Let's put this in perspective. The collapse of a stellar core releases about 10 to the 46th joules of energy in a fraction of a second. That's 10 followed by 46 zeros. To give you a sense of scale, the sun produces about 10 to the 26th joules per second. It would take the sun 100 billion years, far longer than the current age of the universe, to produce as much energy as a single supernova releases in less than a second. And that energy concentrated in such a small volume creates conditions that exist nowhere else. Temperatures of 100 billion degrees, densities where a cubic centimeter weighs as much as a mountain, pressures so intense that atomic nuclei are crushed together, creating isotopes that decay almost instantly, releasing more energy, feeding the explosion. It's a runaway process, a chain reaction of physics operating at its most extreme. And yet, from Earth, when we see a supernova, it looks gentle. A new star appears in the sky, brightening over days, fading over weeks or months. There's no sense of violence, no hint of the chaos that created it. Just light, steady, and distant. The universe has a way of softening its catastrophes across distance. What is destruction up close becomes beauty from far away. Maybe that's a lesson, or maybe it's just the nature of light that it carries energy, but not emotion, that it reaches us unchanged by what it witnessed. There's one more aspect of the collapse we should consider: time dilation. Near the collapsing core, gravity is so strong that time itself slows down relative to an outside observer. If you were somehow watching the collapse from a safe distance, you would see the core's surface falling inward. But as it approaches the event horizon, if it's forming a black hole, the collapse appears to freeze. Light from the surface becomes redshifted, stretched to longer wavelengths, dimming, fading until it disappears entirely. From your perspective, the core seems to take forever to finish collapsing. But from the perspective of the core itself, the collapse happens almost instantly. Time is relative. The collapse is both instantaneous and eternal, depending on where you're standing. Einstein's equations predict this, and observations of black holes forming confirm it. Time near a dying star does not flow the way it does here on Earth. So, what do we take from all this? What does it mean that a star can collapse in a quarter of a second, releasing more energy than it produced in its entire lifetime, creating conditions of temperature and density that we can barely comprehend? Maybe it means that the universe is capable of extremes. We can't fully imagine that the boundaries of physics are far beyond anything we experience in our daily lives. Or maybe it means that even in the most violent events, there is a kind of order, a predictability. The collapse follows equations. Neutrinos escape. The shockwave forms. The star explodes. We can model it, simulate it, predict it. Nature is strange, but it's not random. It follows rules even when those rules produce outcomes that seem impossible. And there's something humbling in that. The fact that we standing on a small planet orbiting an ordinary star can understand what happens inside a collapsing stellar core billions of light years away. We can write equations that describe temperatures of 100 billion degrees. We can detect neutrinos that traveled for 168,000 years just to pass through a tank of water in Japan. We can measure gravitational waves from events so distant that the light hasn't reached us yet. The universe is vast and strange, but it's not beyond our reach. We can listen to it. We can learn its language. And when a star collapses, when gravity wins and a core implodes in a quarter of a second, we can know with precision what happened. That's the quiet power of science. Not to control the universe, but to understand it. But the collapse is only the beginning. The shockwave is still racing outward, tearing through the star's layers, heating them, compressing them, carrying with it all the energy that will soon become light. And when that shockwave finally reaches the surface, when it breaks free into space, the star will become the brightest thing in the sky. Brighter than anything except the sun and moon. Bright enough to cast shadows at midnight. That's what we're moving toward now. The moment when all that violence, all that energy finally becomes visible. The shockwave breaks through. After hours of fighting its way through dense stellar layers, after stalling and reviving, after being pushed forward by ghost particles that barely interact with matter, the shockwave finally reaches the star's surface. And in that moment, the star begins to shine. Not with the steady glow it held for millions of years, but with a brilliance so intense that for a few weeks, a single dying star can outshine an entire galaxy of 100 billion suns. This is the supernova's light. This is what we see from Earth when we say a new star has appeared in the sky. But what makes it so bright? What turns a collapsing core into the most luminous event in the universe? Light at its core is energy. Photons carrying electromagnetic radiation, moving at the fastest speed allowed by physics. When the shock wave reaches the star's surface, it does two things. First, it heats the outer layers to millions of degrees, causing them to emit a flood of photons across the entire spectrum from radio waves to gamma rays. Second, it accelerates those layers outward at speeds of 10 to 15,000 kilometers per second, roughly 3 to 5% the speed of light. This expanding shell of hot gas is what we see glowing. As it expands, it cools, and as it cools, the spectrum of light shifts. Initially, the supernova is brightest in ultraviolet and X-rays. Then it shifts to visible light, the blue and white glow that human eyes can detect. Over weeks and months, it fades to red and infrared, and eventually it becomes invisible to the naked eye, though telescopes can still track it for years. The peak brightness of a supernova is almost incomprehensible. A typical Type 2 supernova, the kind that comes from a massive star collapsing, reaches an absolute magnitude of about 17. That's a technical term astronomers use, but here's what it means in simpler terms. If you place that supernova at the same distance from Earth as the Sun, about 93 million miles away, it would be as bright as the Sun. One exploding star, billions of times farther away than the Sun, shining as brightly as the Sun appears to us. And some supernovae are even brighter. The most luminous ones, called superluminous supernova, can reach absolute magnitudes of 22 or even 23 making them 10 to 100 times brighter than ordinary supernovae. Scientists still don't fully understand what powers these extremes, though theories involve interaction with surrounding material magnetic fields or even exotic forms of energy release that we haven't yet identified. But let's ground this in history and real observations. On April 30th, 1006, AD astronomers across the world noticed something extraordinary. A brilliant new star appeared in the constellation, Lupus, visible in both the northern and southern hemispheres. It was so bright that it cast shadows at night. Historical records from China, Japan, Egypt, Iraq, and Switzerland all mention it. The Chinese court astronomer Zhou Qiming wrote that the star was half the size of the moon and bright enough to illuminate the ground. European monks recorded it in their chronicles, calling it a portent, a sign from the heavens. The star remained visible for months, slowly fading and then disappeared. For nearly 1,000 years, no one knew what it was. Then in the 20th century, astronomers identified the remnant. SN 1006, as it's now called, was a type Ia supernova, a different kind of stellar explosion caused by a white dwarf star in a binary system accumulating too much mass and detonating. It occurred about 7,200 light-years from Earth, meaning the explosion actually happened around 5800 BC, but its light took 7,200 years to reach us. And even from that distance, it was the brightest supernova ever recorded in human history. At its peak, it reached an apparent magnitude of around 7.5, which is about 16 times brighter than Venus at its brightest. You could read a book by its light. Think about that for a moment. An object 7,200 light-years away so far that its light traveled for the entire span of recorded human civilization before reaching Earth, and it was still bright enough to cast shadows. That's the power of a supernova. That's what happens when you compress the energy of a star's entire lifetime into a few weeks of visible light. The photons flooding out from SN 1006 had been created in the violence of the explosion, and they carried that energy across thousands of light years, arriving at Earth in a steady stream, illuminating medieval skies witnessed by people who had no idea they were seeing something that happened before the pyramids were built. Now, let's talk about why astronomers care so much about supernova brightness, because it's not just about spectacle, it's about measurement. In the 1990s, two independent teams of astronomers were studying type Ia supernova, trying to use them as standard candles to measure the expansion rate of the universe. Type Ia supernovae are special because they always explode at roughly the same intrinsic brightness. They occur when a white dwarf, the dense remnant of a sun-like star, accretes material from a companion star and crosses a critical mass threshold, about 1.4 solar masses, the Chandrasekhar limit again. When it reaches that mass, carbon fusion ignites throughout the star almost simultaneously, and the entire white dwarf detonates in a thermonuclear explosion. No core is left behind. The star is completely destroyed. And because the conditions are always roughly the same, a white dwarf exploding at the Chandrasekhar limit, the peak brightness is always roughly the same, about 5 billion times brighter than the sun. Astronomers realized they could use this. If you know how bright something truly is, its absolute magnitude, and you measure how bright it appears from Earth, its apparent magnitude, you can calculate how far away it is. The more distant a supernova, the dimmer it appears, following a precise mathematical relationship called the inverse square law. So the teams began measuring distant type Ia supernovae, expecting to confirm that the universe's expansion was slowing down due to gravity pulling everything back together. Instead, they found the opposite. The distant supernovae were dimmer than expected, meaning they were farther away than expected, meaning the universe was expanding faster in the past than it is now. This was shocking. It implied that the expansion of the universe is accelerating, driven by some unknown force pushing galaxies apart. Scientists called this force dark energy. and it now accounts for about 68% of the total energy content of the universe. The discovery earned the Nobel Prize in Physics in 2011, and it all came from measuring the brightness of exploding stars. So, supernovae are not just bright, they are rulers. They are cosmic yardsticks that let us measure distances across the universe, distances so vast that no other method works reliably. Without supernovae, we wouldn't know how fast the universe is expanding. We wouldn't know about dark energy. We wouldn't understand the large-scale structure of the cosmos. A dying star billions of light years away tells us something fundamental about the fate of everything. But here's something most people misunderstand about supernova brightness. The explosion itself is not what makes them so luminous for weeks or months. The initial shockwave breakout when the shockwave first reaches the star's surface lasts only minutes, maybe hours. It's incredibly bright, but brief. The long-lasting glow, the part that lets us see supernovae for weeks, comes from a different process, radioactive decay. During the explosion, the intense heat and pressure in the shockwave create radioactive isotopes, particularly nickel-56 and cobalt-56. These isotopes are unstable. Nickel-56 has a half-life of about 6 days, meaning half of it decays into cobalt-56 within 6 days. Cobalt-56 then decays into stable iron-56 with a half-life of about 77 days. Each decay releases gamma rays, high-energy photons that heat the expanding debris from the inside. This heat makes the debris glow. As the nickel decays into cobalt and the cobalt decays into iron, the supernova's brightness follows a predictable curve, peaking a few weeks after the explosion and then fading gradually over months. Astronomers call this the light curve, and by analyzing its shape, they can learn about the explosion's energy, the amount of radioactive material produced, and even the structure of the progenitor star. There's a beautiful symmetry here. The same nuclear processes that powered the star during its life fusion creating heavier elements are also responsible for its lingering death glow. Radioactive decay. The breakdown of unstable nuclei releases energy in the form of light. The star shines in death, as it did in life, but for different reasons. In life, it was fusion pushing outward. In death, it's decay heating the ruins. Let's compare this to something more familiar. When you see a firework explode in the night sky, the initial flash is bright but brief. What lingers, what creates the patterns and colors you admire, is the burning of metal salts, strontium for red, barium for green, copper for blue. The explosion disperses the chemicals and they burn as they fall. A supernova is similar, but on an unimaginably larger scale. The explosion scatters radioactive material across light years, and that material glows as it decays, painting the cosmos with light that lasts not seconds, but months. Every photon you see from a supernova weeks after the explosion is powered by a nucleus transforming, giving up energy, settling into stability. Now, there are different types of supernovae, and they shine differently. We have mentioned type Ia, the white dwarf explosions, but there's also type 2, the core collapse supernovae from massive stars. Type 2 supernovae tend to be less luminous than type Ia, though still extraordinarily bright. Their light curves are different too. Type 2 supernovae often show a plateau, a period where the brightness stays relatively constant for weeks or months before declining. This happens because the expanding debris is still thick enough to trap heat, and hydrogen in the outer layers recombines, releasing energy slowly. It's like a glowing ember cooling down, except the ember is several solar masses of hydrogen expanding at thousands of kilometers per second. Then there are the superluminous supernovae, the SLS&E discovered in the early 2000s. These are rare, perhaps 1 in 10,000 supernovae, but they are staggeringly bright, up to 100 times brighter than ordinary supernovae. Some of them show no hydrogen in their spectra, suggesting the progenitor star lost its outer layers before exploding. Others show hydrogen, but in unusual amounts. Scientists have proposed several mechanisms to explain them. One idea is that they involve magnetars neutron stars with magnetic fields trillions of times stronger than Earth's. If a magnetar forms during the collapse and spins rapidly, its magnetic field can deposit enormous amounts of energy into the expanding debris, making it shine far brighter than expected. Another idea is that the explosion interacts with a dense shell of material ejected by the star before it exploded, converting kinetic energy into light. We're still learning. Every superluminous supernova observed adds to the puzzle, and the full picture isn't yet clear. There's also something called a kilonova, a related but distinct event. When two neutron stars collide and merge, they produce a burst of light powered not by radioactive nickel and cobalt, but by the rapid decay of even heavier elements, including gold, platinum, and uranium. Kilonovae are fainter than supernovae, lasting only days instead of weeks, but they are significant because they produce most of the universe's heaviest elements. The first kilonova, detected with both gravitational waves and light, occurred in 2017, observed by thousands of astronomers around the world. It was a landmark event, the beginning of multi-messenger astronomy, combining gravitational waves, light, and even neutrinos to study cosmic explosions. But that's a tangent. We're here for supernovae, for stars that explode alone, not in pairs. Let's return to brightness and what it means. When you see a supernova, when you look at images from Hubble or James Webb, showing a bright point of light in a distant galaxy, you're seeing energy that traveled unimaginable distances to reach your eyes. That light left the supernova weeks or months after the explosion, when the debris was still hot, still glowing from radioactive decay. It traveled through intergalactic space, a void so empty that it might contain one atom per cubic meter for millions or billions of years. It passed through dust clouds that absorbed some wavelengths and let others through. It was redshifted by the expansion of the universe, stretched to longer wavelengths as space itself expanded. And then finally it entered. The telescope was focused onto a detector, converted into an electrical signal, processed into an image, and displayed on your screen. The photon's journey from the heart of an exploding star to your eye is one of the longest possible journeys in the universe. And the fact that we can trace that journey, that we can look at a supernova billions of light years away, and understand not just that it's bright, but why it's bright, how the light was produced, what elements are glowing, how fast the debris is moving. That's extraordinary. Here's a question to sit with. When you look at a supernova, are you seeing the past or the present? The light left the star long ago, perhaps, when dinosaurs roamed the Earth, or before the Earth even existed. But the photons are reaching you now in this moment. Is the supernova a past event or a present experience? Relativity doesn't give a clear answer. For the photon traveling at the speed of light, no time passes at all. The photon is emitted and absorbed in the same instant from its perspective. But from your perspective, from Earth, millions of years have passed. Time is not absolute. It depends on where you are and how fast you're moving. A supernova is both ancient and immediate, both history and happening now. And maybe that's the most profound part of supernova brightness. It's not just that they're luminous, it's that their light connects us to events we could never witness directly. We can't travel to distant galaxies. We can't go back in time. But the light does both for us. It brings the past into the present. It carries information across gulfs so vast that they defy human comprehension. And when we catch that light, when we study it, measure it, understand it, we are touching something that happened unimaginably far away and long ago. We are making the universe smaller, not in size, but in intimacy. We are learning to read its language one photon at a time. So, the next time you hear about a supernova, remember this. You're not just hearing about an explosion. You're hearing about a message sent across the universe in the form of light, carrying information about temperature, composition, velocity, distance, and time. That message took eons to arrive. And we are here now with the tools and knowledge to read it. That's the quiet power of supernova brightness, not just to shine, but to speak. But brightness is only part of the story. The light tells us what happened, but it doesn't tell us what the supernova left behind. Because within that expanding cloud of gas, within the debris still glowing from radioactive decay, something is forming. Elements. Not just any elements, but the heavy ones, the ones that couldn't exist before. The ones that will someday build planets' atmospheres and life. That's where we turn next, to the forge, to the place where everything you touch was born. Look at your hand for a moment. The skin, the bones beneath the blood flowing through your veins. Every atom in your body has a history longer than you can imagine. The carbon that forms the backbone of your DNA, the calcium that gives your bones their strength, the iron in your hemoglobin, carrying oxygen to your cells. None of these existed at the beginning of the universe. They were created, not in a laboratory, not through any process we can replicate on Earth, but in the hearts of dying stars, in the violence of supernovae. You are made of elements forged in explosions so powerful they briefly outshone galaxies. And tonight, we're going to trace that journey from the moment of the Big Bang to the atoms in your hand. In the beginning, the universe was simple, painfully simple. When the Big Bang occurred, 8 billion years ago, the universe was a hot, dense soup of fundamental particles, quarks and electrons and photons, all moving at incredible speeds, colliding, separating, colliding, again. As the universe expanded and cooled, those quarks combined to form protons and neutrons. And about 3 minutes after the Big Bang, when the temperature had dropped to around 1 billion degrees, Kelvin nuclear fusion began. Protons and neutrons started sticking together, forming the nuclei of the lightest elements. Hydrogen, just a single proton. Deuterium, a proton and a neutron. Helium-3, 2 protons and 1 neutron. Helium-4, 2 protons and 2 neutrons. And trace amounts of lithium-7, 3 protons and 4 neutrons. That's it. That's all the Big Bang nucleosynthesis produced. About 75% hydrogen, 25% helium, and a tiny fraction of lithium. No carbon, no oxygen, no iron, no gold. The universe, for all its size and energy, was chemically boring. For hundreds of millions of years, the universe stayed that way. Hydrogen and helium gas clouds drifting through darkness, cooling, clumping together under gravity. Then, eventually, the first stars formed. Massive, hot, short-lived stars made entirely of hydrogen and helium. Astronomers call them population 3 stars, and none have ever been directly observed because they all died long ago. But we know they existed because we see their descendant stars made from the material they scattered into space. These first stars began the process of building complexity. In their cores, hydrogen fused into helium. Then when the hydrogen ran out, helium fused into carbon and oxygen. And for the first time in the universe's history, there were atoms heavier than lithium. The periodic table began to grow, but carbon and oxygen were just the beginning. As these massive stars continued burning, they produced heavier and heavier elements layer by layer, following the same process we discussed earlier. Carbon fused into neon and magnesium. Oxygen fused into silicon and sulfur. Silicon fused into iron. And when the iron core formed, the star collapsed and exploded, scattering all those newly created elements into space. The first supernovae seeded the universe with the raw materials for planets, for chemistry, for life. Without those explosions, we wouldn't exist. There would be nothing but hydrogen and helium forever. Now, here's where it gets even more interesting. Iron is the endpoint of fusion in a star's core, the element where you stop gaining energy from fusing nuclei together. But iron is not the heaviest element. There are 26 protons in an iron nucleus. The periodic table goes up to 118 and beyond. So, where do the rest of the elements come from? How do you make gold with 79 protons? Or uranium with 92 protons? Or lead or platinum or silver? The answer lies in the supernova itself, in the explosion in the shock wave and the extreme conditions it creates. This is called explosive nucleosynthesis, and it's one of the most violent and creative processes in the universe. When the shock wave tears through the star's layers, the temperature and pressure spike to unimaginable levels. Nuclei are bombarded with neutrons particles with no electric charge that can slip into atomic nuclei without being repelled. There are two main pathways for building heavy elements through neutron capture. The first is the S process, the slow process which happens inside massive stars during their lives, not during the explosion. In the S process, a nucleus captures a neutron, and if that makes the nucleus unstable, it decays, turning a neutron into a proton and emitting an electron. Then it captures another neutron and decays again. Slowly, step by step, the nucleus climbs the periodic table. This process can produce elements up to about bismuth element 83, but it's too slow and gentle to go much further. The second pathway is the RR process, the rapid process, and this only happens in the most extreme environments. Supernovae, neutron star mergers, places where the neutron density is so high that nuclei are hit by multiple neutrons in rapid succession, faster than they can decay. A nucleus might capture 10, 20, 50 neutrons in a fraction of a second, becoming wildly unstable, then decaying in a cascade, releasing electrons and neutrinos, stabilizing into a heavy element that wouldn't exist otherwise. The R process is how nature makes gold, platinum, uranium, thorium, and all the elements heavier than iron that the S process can't reach. And it only works in conditions that are quite literally explosive. Let's focus on gold for a moment, because gold has a special place in human history, and its origin story is extraordinary. Gold has 79 protons. To make gold, you need to start with something lighter, and add protons, which means converting neutrons into protons through radioactive decay after capturing those neutrons. This requires a neutron-rich environment, high temperatures, and extreme densities. For most of history, scientists assume supernovae were the primary source of gold in the universe. And they are a source, but recent observations suggest that neutron star mergers might be even more efficient at producing gold. In 2017, when LIGO detected gravitational waves from two neutron stars colliding and telescopes observed the resulting kilonova, spectroscopic analysis of the light reveals signatures of heavy elements, including gold and platinum. Scientists estimate that this single collision produced several Earth masses worth of gold, perhaps 10 times the mass of Earth, all created in a few seconds of unimaginable violence. But supernovae still contribute. Every supernova scatters elements into space, and over billions of years, those elements mix with clouds of hydrogen and helium, enriching them, making them chemically diverse. The solar system formed from one such cloud about 4.6 billion years ago. That cloud contained hydrogen and helium from the Big Bang, but it also contained carbon, oxygen, silicon, iron, and trace amounts of heavier elements like gold, all of which came from previous generations of stars that lived, died, and exploded long before the sun existed. When the cloud collapsed under gravity, the densest part became the sun, and the remaining material flattened into a disk. In that disk, dust grains formed tiny particles made of silicates, iron, carbon compounds, and ice. Those grains stuck together, forming pebbles, then rocks, then planetesimals, and eventually planets. Earth is made of stardust. Every rock, every ocean, every living thing built from atoms, forged in supernovae. Here's a startling fact. Scientists have analyzed meteorites, ancient rocks that fell to Earth from space, and found isotopes that only form in supernovae. One example is iron-60, a radioactive isotope of iron with a half-life of 2.6 million years. Iron-60 doesn't occur naturally on Earth anymore because it's decayed away, but scientists have found traces of it in deep-sea sediments in layers that date back about 2 to 3 million years. This suggests that a supernova exploded relatively nearby within a few hundred light years, sometime in the past few million years. and the debris from that explosion drifted through the solar system, depositing iron-60 on Earth. We were dusted by a dead star. The evidence is in the mud at the bottom of the ocean. There's also another isotope worth mentioning, plutonium-244. This is a heavy element with a half-life of 80 million years. It's been found in trace amounts in ancient rocks and deep-sea crusts, far more than could be explained by natural radioactive decay on Earth. The only plausible source is supernovae. Multiple supernovae actually exploding at different times, scattering plutonium across the galaxy, some of which eventually made its way to Earth. These isotopes are like fingerprints. They tell us that the solar system has been bathed in supernova debris for billions of years, that we live in a dynamic, violent galaxy where stars explode regularly and their remains travel across vast distances, mixing with everything. Let's think about this on a more personal level. The calcium in your bones, about 1 kilogram for an average adult, came from supernovae. Calcium has 20 protons. It's produced in the oxygen-burning and silicon-burning shells of massive stars, then scattered into space when the star explodes. Billions of years later, some of those calcium atoms ended up in the dust cloud that formed Earth, then in the rocks and soil, then in plants, then in animals, and eventually in you. The iron in your blood, about 4 grams in total, came from the same process. Iron is the final product of fusion, the element that signals a star's death. And now it's in your hemoglobin, binding to oxygen, keeping you alive. You are breathing using atoms that once marked the end of a star. And the carbon. Every organic molecule in your body, your DNA, your proteins, your fats, all of it built on a skeleton of carbon atoms. Carbon has 6 protons. It's produced in the helium-burning shells of red giants and scattered into space when those stars shed their outer layers or explode. Carl Sagan famously said, "We are made of star stuff." And he was right, but the phrase sometimes gets romanticized, stripped of its literal truth. We are not metaphorically made of star stuff. We are literally made of star stuff. Every single atom in your body, except for hydrogen, was created inside a star or in a supernova. The hydrogen might be original, left over from the Big Bang, but everything else is recycled stellar material. You are a collection of atoms that have existed for billions of years, cycling through stars, through space, through planets, through living things, and now through you. There's a common misconception that needs clearing up. People sometimes think that all elements are made in supernovae. That's not quite right. Light elements up to iron are made through fusion in the cores and shells of stars during their lives. The star doesn't need to explode to produce carbon, oxygen, or iron. But the star does need to explode to scatter those elements into space to make them available for the next generation. Without the explosion, the elements would stay locked inside the star, eventually collapsing into a neutron star or black hole, never contributing to planets or life. So supernovae are both forges and distributors. They create the heaviest elements through explosive nucleosynthesis, and they scatter the lighter elements that were created earlier. There's also another subtlety. Not all stars become supernovae. Stars like the Sun, with masses less than about 8 times the Sun's mass, die more gently. They swell into red giants, shed their outer layers in a process called a planetary nebula, and leave behind a white dwarf. These stars contribute to the chemical enrichment of the galaxy, but not through supernovae. They produce carbon, nitrogen, and some heavier elements through the S process, and they release those elements slowly over thousands of years as their outer layers drift away. It's a quieter death, but still important. The universe builds complexity through multiple pathways, not just explosions. But for the heavy elements, for gold and platinum and uranium, you need the violence. You need conditions so extreme that neutrons are flying around in vast numbers, smashing into nuclei, building up heavy isotopes that immediately decay, releasing energy, creating new elements that don't exist in nature on Earth except in trace amounts. These elements are rare because the conditions that create them are rare. A supernova happens in our galaxy once or twice per century. A neutron star merger is even rarer, perhaps, once every few thousand years in a galaxy like ours. So, when you hold a gold ring, you're holding something that required a cosmic catastrophe to create. It's not just valuable because it's pretty, or because people decided it was valuable. It's valuable because it's genuinely rare, created in events so extreme that they happen only a handful of times in the history of a galaxy. Here's another way to think about it. The universe is a story of increasing complexity. It starts with the simplest elements, hydrogen and helium, and over billions of years through the lives and deaths of stars, it builds up a periodic table. Each new generation of stars is made from material enriched by the previous generation. The first stars were pure hydrogen and helium. The second generation contained traces of carbon and oxygen. The third generation, which includes our sun, contains small amounts of almost every element. And future generations, billions of years from now, will contain even more heavy elements because more stars will have died and scattered their contents. The universe is slowly becoming richer, more diverse, more capable of forming complex structures like planets and life. And supernovae are the engines of that transformation. There's a poetic irony here. The elements that make life possible, carbon, nitrogen, oxygen, phosphorus, sulfur, are produced in the calm, steady burning of stars over millions of years. But those elements remain useless, locked away inside stars unless something violent happens. A supernova is an act of destruction that enables creation. The star dies so that its atoms can be reborn as something new. It's a cycle, a rhythm of birth and death played out on cosmic scales. Nothing is permanent. Everything is recycled. The atoms in your body have been part of other things before. Maybe they were in another star, or a comet, or a microbe in the primordial ocean. And someday they'll be part of something else. The universe doesn't waste anything. Scientists can trace this cycle by studying the chemical composition of stars. Older stars, formed billions of years ago, have lower abundances of heavy elements, what astronomers call low metallicity. Younger stars, formed more recently, have higher metallicity because they form from gas clouds enriched by many generations of supernovae. By measuring the ratio of different elements in a star's spectrum, astronomers can estimate when and where it formed, how many supernovae had occurred before it, and what the chemical history of its neighborhood was. It's like reading a star's family tree written in light. And here's a question that might make you pause. If we are made of supernova debris, and supernovae are rare, does that make us rare too? It's hard to say. The Milky Way has about 200 to 400 billion stars, and supernovae have been occurring for billions of years, so there's been plenty of time for heavy elements to spread throughout the galaxy. But not all regions of the galaxy are equally enriched. The outer edges far from the dense star-forming regions have fewer heavy elements because fewer supernovae have occurred there. The center of the galaxy, on the other hand, is rich in heavy elements but also bathed in intense radiation from the supermassive black hole and densely packed stars. Earth formed in what astronomers call the galactic habitable zone, a region where there are enough heavy elements to build rocky planets, but not so much radiation that life would be sterilized. We are in the right place at the right time, made of the right stuff. Whether that's common or rare across the universe, we don't yet know. But it's certainly not random. Every breath you take, every word you speak, every thought you think depends on elements created in the hearts of dying stars. Oxygen produced in massive stars and scattered by supernovae. Carbon forged in red giants and released in their final gasps. Nitrogen created through cycles of fusion and mixing in stellar interiors. These are not abstractions. These are the literal building blocks of your body, your brain, your existence. You are not separate from the universe. You are a part of it, made from its history, shaped by its laws, participating in its unfolding story. And that story is still being written one supernova at a time, one atom at a time, slowly building the complexity that makes everything possible. But there's more to the story than just creation. Because after the explosion, after the elements are scattered, something remains. Remnants, clouds of gas glowing in the aftermath, expanding for thousands of years. And sometimes at the center, a dense object, a neutron star or a black hole spinning, radiating quietly, continuing the work of the dead star. That's where we're heading next. Into the remnants, into the echoes left behind, when a star gives everything away and still manages to leave a mark. When the light fades, when the supernova dims and disappears from view, most people think the story is over. The star exploded, scattered its atoms, and vanished into the darkness. But that's not quite true. Something remains, not just debris, not just expanding gas, but structures, objects, phenomena that can last for thousands, even millions of years. Supernova remnants are the ghosts of dead stars, still glowing, still evolving, still shaping the space around them. And at the center, sometimes there is a core, a remnant of the remnant, something so dense, so strange that it defies ordinary intuition. A neutron star, or if the original star was massive enough, a black hole. These are the final signatures of a star's life, written in matter so compressed that the rules of physics bend and break. Let's begin with the most famous supernova remnant in history, one that has been observed and studied for nearly 1,000 years. On July 4th, 1054, 80 Chinese astronomers recorded the appearance of a guest star in the constellation Taurus. It was so bright that it was visible during the day for 23 days, and at night for nearly 2 years. Historical records from Japan and the Arab world also mention it, though curiously there are no definitive European records, which has puzzled historians. This guest star was a supernova, and what it left behind is now called the Crab Nebula, one of the most studied objects in the night sky. The Crab Nebula is a cloud of gas about 11 light-years across, still expanding outward from the explosion at a speed of about 1,500 kilometers per second. When you look at images of it, you see delicate filaments, glowing threads of hydrogen, helium, oxygen, and other elements illuminated by radiation from the core. The colors in those images aren't random. Red light comes from hydrogen and sulfur. Green comes from oxygen. Blue comes from helium. Each element emits light at specific wavelengths when it's energized. And by analyzing those wavelengths, astronomers can map the chemical composition of the nebula, measuring how much of each element was produced in the explosion, how it's distributed, how fast it's moving. The Crab Nebula is a laboratory, a place where we can study the aftermath of a supernova in exquisite detail. But here's what makes the Crab Nebula truly extraordinary at its center. There is a pulsar. A pulsar is a type of neutron star that spins rapidly and emits beams of radiation from its magnetic poles. As it spins, those beams sweep across space like a lighthouse. And if one of those beams happens to point toward Earth, we see a pulse of light. The Crab pulsar, designated PSR B0531-21, spins 30 times per second. Every 33 milliseconds, it completes one full rotation, and we see a flash of light across the electromagnetic spectrum, from radio waves to gamma rays. This pulsar is what powers the nebula's glow. It's like a cosmic generator pumping energy into the surrounding gas, keeping it bright long after the explosion itself has ended. Neutron stars are among the strangest objects in the universe. Imagine taking the mass of the Sun, 2 times 10 to the 30th kilograms, and compressing it into a sphere about 20 kilometers across, roughly the size of a city. The density is almost incomprehensible. A single teaspoon of neutron star material would weigh about 10 million tons, roughly the weight of Mount Everest. At that density, atoms no longer exist. Electrons and protons have been squeezed together to form neutrons, and those neutrons are packed so tightly that they touch, creating a form of matter that doesn't exist anywhere else in the universe, except possibly at the cores of other neutron stars. Scientists call this neutron degenerate matter, and its properties are still not fully understood. The surface of a neutron star is thought to be a crystalline crust made of iron nuclei, arranged in a lattice, but not like any iron you've ever touched. It's iron compressed to densities where the atomic structure itself changes. Below the crust, there are layers of increasingly strange matter, neutron-rich nuclei, free neutrons, and deeper still exotic forms of matter that might include hyperons, particles made of strange quarks, or even deconfined quark matter, where neutrons break down into their constituent quarks. No laboratory on Earth can recreate these conditions. Neutron stars are natural physics experiments testing the limits of what matter can do under extreme pressure. And then there's the magnetic field. Some neutron stars, especially young ones, have magnetic fields trillions of times stronger than Earth's. These are called magnetars, and they are the most magnetic objects known to exist. A magnetar's magnetic field is so strong that it warps the vacuum of space itself, creating virtual particle-antiparticle pairs that flicker in and out of existence. If you were somehow standing on the surface of a magnetar, which you absolutely couldn't, because you'd be torn apart by tidal forces, the magnetic field would be strong enough to disrupt the molecular bonds in your body. It would literally pull the atoms apart. Magnetars occasionally release bursts of energy called starquakes, where the crust of the neutron star cracks and shifts, releasing more energy in 1/10 of a second than the sun produces in a year. But let's return to pulsars, because they were one of the greatest discoveries in 20th century astronomy. In 1967, a graduate student named Jocelyn Bell Burnell was working with a radio telescope at Cambridge University, studying the twinkling of distant radio sources caused by the solar wind. One night she noticed something unusual, a series of regular pulses arriving every 1.33 seconds, far too precise to be natural. At first, the team jokingly referred to the signal as LGM1 for little green men, because it seemed almost like an artificial beacon. But they quickly found more pulsars, and it became clear these were natural objects, not extraterrestrial transmissions. The discovery was groundbreaking. It confirmed the existence of neutron stars, which had been predicted theoretically, but never observed. In 1974, the Nobel Prize in Physics was awarded for the discovery of pulsars, but controversially, it went to Jocelyn Bell's supervisor and not to Bell herself, despite the fact that she made the initial observation. It's one of the most famous examples of the Matilda effect, where women's contributions to science are overlooked or attributed to male colleagues. Pulsars are incredibly precise timekeepers. The most stable pulsars, called millisecond pulsars, spin hundreds of times per second, and their rotation is so regular that they rival atomic clocks in accuracy. Astronomers use pulsars as cosmic metronomes, tools for testing general relativity, searching for gravitational waves, and even navigating spacecraft. There's a proposal to use pulsars as a kind of galactic GPS, where a spacecraft could determine its position in the galaxy by measuring the timing of pulses from multiple pulsars triangulating its location. The universe in its own way provides tools we can use. But not all supernova remnants are as orderly as the Crab Nebula. Some are chaotic, asymmetric, shaped by interactions with surrounding gas or by the explosion itself. Take Cassiopeia A, for example. This is the remnant of a supernova that occurred about 340 years ago, around 1680, though oddly no historical records exist of anyone seeing it. That might be because the progenitor star was shrouded in dust, which dimmed the visible light, but allowed infrared and radio emissions to escape. Cassiopeia A is one of the brightest radio sources in the sky, and images from telescopes like Chandra and Spitzer reveal intricate structures, knots of silicon sulfur, calcium, and iron, each moving at different speeds, each telling a piece of the explosion story. At the center, there's likely a neutron star, though it's difficult to detect because it doesn't pulse like the Crab pulsar. It's just sitting there, cooling, radiating, faintly almost invisible against the glowing debris around it. Supernova remnants evolve through several phases over thousands of years. Initially, the shockwave from the explosion races outward, heating the surrounding gas to millions of degrees, creating a blast wave that glows in X-rays. This is the free expansion phase where the debris is moving so fast that nothing can stop it. Eventually, though, the shockwave slows down as it plows into more and more interstellar material, sweeping it up, compressing it. This is called the Sadov-Taylor phase, and it can last tens of thousands of years. The remnant becomes a shell, a bubble of hot gas expanding into the cooler, surrounding medium. Finally, the remnant cools and fades, merging with the interstellar medium, becoming indistinguishable from the background. But the heavy elements it carried remain mixing with the gas, enriching it, ready to be incorporated into the next generation of stars. There's a particularly beautiful example of this process in the constellation Cygnus, a region called the Cygnus Loop, or the Veil Nebula. This is a supernova remnant between 5,000 and 10,000 years old, appearing as delicate lace-like filaments stretching across several degrees of the sky. The colors and images of the Veil Nebula are stunning reds and blues and greens, each representing different elements being excited by the shockwave. It's a reminder that even in death, even in destruction, there is beauty. The universe doesn't distinguish between creation and destruction. It simply transforms endlessly everything into something else. Now, let's talk about what happens when the core is too massive for even neutron degeneracy pressure to stop the collapse. When the core exceeds about 3 solar masses, nothing can resist gravity. The collapse continues past the neutron star stage, past any known form of matter, and the core becomes a black hole. A black hole is not an object in the traditional sense. It's a region of space-time where gravity is so strong that not even light can escape. The boundary of this region is called the event horizon, and once something crosses it, it's gone cut off from the rest of the universe. Information cannot escape. Light cannot escape. Time itself, from an outside perspective, appears to stop at the event horizon. Black holes formed from supernovae are called stellar mass black holes, and they typically range from about 3 to several dozen solar masses. They're invisible by definition because they don't emit light, but they can be detected indirectly through their gravitational effects on nearby objects. If a black hole is in a binary system with a normal star, it can pull gas from the companion star, and that gas forms an accretion disk, spiraling inward, heating up to millions of degrees, and emitting X-rays before it crosses the event horizon. Astronomers have identified dozens of stellar mass black holes this way, including famous systems like Cygnus X1, the first black hole ever confirmed, discovered in the early 1970s. There's something deeply strange about black holes that most people don't fully grasp. From the perspective of an outside observer, an object falling toward a black hole never actually crosses the event horizon. As it gets closer, time dilation becomes more extreme, and the object appears to slow down its light, redshifting, fading, freezing in place just above the horizon. From the perspective of the infalling object, though it crosses the horizon in finite time, experiencing nothing unusual at that moment, though it will inevitably be torn apart by tidal forces, as it approaches the singularity at the center. This is the paradox of black holes. They are both endpoints and gateways, both frozen and dynamic, both simple and infinitely complex. Einstein's equations predict that at the center of a black hole, there is a singularity, a point of infinite density where space-time curvature becomes infinite and the equations break down. But most physicists believe this is a sign that our understanding is incomplete, that at some scale, quantum mechanics must take over and smooth out the singularity into something less pathological. String theory, loop, quantum gravity, and other approaches to quantum gravity all suggest that singularities might not be truly infinite, that there's some minimum scale, some quantum structure to space-time that prevents density from becoming infinite. But we don't yet have a complete theory of quantum gravity. So the true nature of what's inside a black hole remains one of the great unsolved mysteries in physics. Supernova remnants. Whether they contain neutron stars or black holes continue to influence their surroundings for millennia. The shock waves from supernova explosions compress nearby gas clouds, triggering the formation of new stars. This is called triggered star formation, and it's thought to be responsible for many of the star clusters we see in the galaxy. The Orion Nebula, for example, a massive star-forming region about 1/300 light-years away, shows signs of being influenced by past supernovae. The compression from those explosions may have initiated the collapse of gas clouds, leading to the birth of the bright young stars we see today. In this way, supernovae don't just destroy, they also create. They seed the next generation. There's also a fascinating connection between supernova remnants and cosmic rays. Cosmic rays are high-energy particles, mostly protons that travel through space at nearly the speed of light. They bombard Earth, constantly colliding with atoms in the upper atmosphere, creating showers of secondary particles. For decades, scientists wondered where cosmic rays came from, and the leading theory is that they're accelerated in the shock waves of supernova remnants. The turbulent magnetic fields in those shock waves can trap particles and accelerate them to enormous energies through a process called diffusive shock acceleration. Observations from X-ray telescopes have found evidence of this process in several supernova remnants, including the one in Tycho's supernova. Cosmic rays are another legacy of dying stars, another way that supernovae shape the galaxy. Here's something to consider. Every supernova remnant is a monument. It's a structure that persists long after the event that created it, a visible marker of a star's death, slowly fading but never forgotten. We can look at these remnants through telescopes and trace their history, measure their composition, calculate when the explosion occurred. They're like fossils, except instead of being buried in rock, they're written in light and gas in the motion of particles across space. The universe keeps records. It remembers. And those records tell us that supernovae are not rare anomalies. They're part of the regular rhythm of the galaxy. In the Milky Way, a supernova occurs roughly once or twice per century on average, though we haven't seen one with the naked eye since 1604 Kepler's supernova. That might seem like a long drought, but it's partly due to chance and partly due to dust obscuring our view of distant parts of the galaxy. In other galaxies, we see supernovae regularly, several per year, in large galaxies, and we study them, measure them, learn from them. Each one adds to our understanding. Each one is a data point in the story of how stars die and how the universe evolves. But supernovae don't just shape the galaxy chemically and physically. They also shape the conditions for life. The heavy elements they produce make rocky planets possible. The shock waves they create compress gas clouds and trigger star formation. The energy they release stirs the interstellar medium, preventing it from settling into a static, lifeless state. Without supernovae, the galaxy would be a much quieter, simpler, less interesting place. And life, if it existed at all, would be very different. We owe our existence in a very real sense, not just to the sun's steady warmth, but to the violence of stars that died billions of years ago. So, when you think of a supernova remnant, don't think of it as just the end of a story. Think of it as a chapter in a longer narrative, a narrative that includes the star's birth, its life, its death, and the legacy it leaves behind. The remnant is still active, still evolving, still contributing to the galaxy's ongoing transformation. And at its center, if there's a neutron star, it spins, pulses, radiates a lighthouse in the darkness. A beacon that says something was here, something burned, something gave itself away, and something remains. But remnants and neutron stars and black holes are only part of the legacy. There's another connection, one that hits closer to home, one that ties supernovae directly to our planet, to our history, perhaps even to our existence. Because supernovae don't just create elements and scatter them into space, they also affect planets' atmospheres and life itself. And that's the thread we're picking up now, the connection between dying stars and the living world. Imagine standing outside on a clear night, looking up at the stars, unaware that invisible particles are passing through your body at that very moment. Not just photons, not just neutrinos from the sun, but high-energy cosmic rays accelerated by supernova shockwaves thousands of light years away. These particles collide with atoms in the upper atmosphere, creating cascades of secondary particles that shower down to the surface. Most pass through you harmlessly. A few interact with your DNA, causing mutations that are usually repaired, but occasionally aren't. Supernovae in this quiet, invisible way are touching you right now. They have been since you were born. They always will be. The question is not whether supernovae affect life on Earth. The question is how much, and whether that influence has ever crossed the line from gentle touch to catastrophic blow. For most of Earth's history, supernovae have been distant spectacles, beautiful but harmless. A star explodes on the other side of the galaxy. Its light reaches Earth, and we see a bright new point in the sky for a few weeks or months. No harm done. The distance protects us. Space is vast, and even the most powerful explosion loses its intensity as it spreads across light years. But distance is not an absolute shield. If a supernova occurs close enough within a certain radius, the radiation it emits can have real measurable effects on a planet's atmosphere, climate, and life. Scientists call this radius the kill zone, and for a supernova, it's estimated to be somewhere between 25 and 30 light years, depending on the type of explosion and the planet's atmospheric composition. Within that radius, a supernova becomes more than a light show. It becomes a threat. Here's what would happen if a supernova exploded within 30 light years of Earth. First, there would be the light and intense burst of ultraviolet and X-ray radiation arriving within hours or days of the explosion. This radiation would not reach the surface directly, because Earth's atmosphere absorbs most of it. But it would interact with the upper atmosphere, breaking apart molecules, ionizing gases, creating chemical reactions that wouldn't normally occur. The ozone layer, which shields the surface from harmful ultraviolet radiation from the sun, would be partially destroyed. For months, maybe years, the ozone hole would allow more UV light to reach the surface, increasing rates of skin cancer, in humans damaging phytoplankton, in the oceans, disrupting food chains. Plants would struggle with increased UV exposure, ecosystems would shift. It wouldn't be an instant apocalypse, but it would be a prolonged stress, a slow degradation of the conditions that make Earth habitable. Then months or years later, there would be the cosmic rays. High-energy particles from the supernova, traveling at nearly the speed of light, would begin to arrive in increasing numbers. These particles would penetrate deeper into the atmosphere, ionizing the air, creating nitrogen oxides that further deplete the ozone layer. The increased ionization would also seed cloud formation, potentially altering weather patterns, cooling the climate, triggering ice ages. There's a hypothesis not yet proven, but supported by some evidence that past ice ages on Earth were influenced by nearby supernovae. The timing is difficult to pin down because supernova remnants fade and disperse over thousands of years, but the idea is plausible. A supernova within 30 light years could cool the planet enough to shift climate patterns, reduce biodiversity, and contribute to extinction events. Now, let's talk about evidence. Scientists have found traces of supernova activity in Earth's geological record. One of the most compelling pieces of evidence comes from deep-sea sediments collected from the ocean floor. In layers dating back about 2 to 3 million years, researchers found elevated levels of iron-60, a radioactive isotope that doesn't occur naturally on Earth and has a half-life of 2.6 million years. The only plausible source for this iron-60 is a supernova. The isotope was created in the explosion, scattered into space, and eventually drifted into the solar system, settling into the oceans as tiny particles of dust. The concentration of iron-60 suggests that the supernova was relatively nearby, perhaps 100 to 300 light years away, far enough that it didn't cause immediate catastrophic damage, but close enough that its debris reached Earth. Interestingly, This time period, around 2 to 3 million years ago, coincides with a period of climate change on Earth. The Pliocene-Pleistocene transition, when Earth's climate cooled, ice sheets began to form, and the environment shifted toward the Ice Age cycles we see in more recent history. Could the supernova have contributed to this cooling? It's possible. The increased cosmic ray flux from the supernova could have seeded more clouds reflecting more sunlight back into space, lowering global temperatures. This is still a hypothesis, and the climate system is complex with many factors contributing to long-term changes. But the timing is suggestive. The universe, it seems, doesn't just provide the building blocks for life. It also influences the conditions in which life evolves, sometimes gently, sometimes harshly. There's another layer of iron-60 in the geological record, this one dating back about 6 to 7 million years. Again, the only explanation is a supernova, and again the concentration suggests it was relatively nearby. Multiple supernovae over millions of years have dusted Earth with their debris. We live in a dynamic galaxy where stars are constantly being born and dying, and occasionally one of them dies close enough that we feel the effects. Not catastrophically, but measurably. The iron-60 in those sediments is a fingerprint, a reminder that Earth is not isolated from the rest of the galaxy. We are part of a larger system influenced by events happening light years away. But let's go further back in time to one of the most mysterious and devastating extinction events in Earth's history. The late Devonian extinction, which occurred about 375 million years ago, wiped out roughly 75% of all species on Earth, particularly marine life. The cause of this extinction has been debated for decades. Some scientists point to volcanic activity, others to changes in ocean chemistry or sea level. But there's another hypothesis, one that connects the extinction to a supernova. In 2002, a team of researchers proposed that a supernova, or a series of supernovae occurring within a few dozen light years of Earth, could have caused the ozone layer to collapse, allowing lethal levels of ultraviolet radiation to reach the surface. Marine organisms, particularly those living in shallow water, would have been the most vulnerable, which matches the fossil record. The hypothesis is supported by the discovery of plant spores from that time period, showing evidence of UV damage, abnormal pigmentation, and mutations consistent with increased radiation exposure. The challenge with this hypothesis is the lack of direct evidence. Unlike the iron-60 deposits from a few million years ago, there are no clear supernova markers in rocks from 375 million years ago. Isotopes decay, remnants disperse, and geological processes erase traces. But the circumstantial evidence is intriguing. The extinction pattern, the timing, the type of damage to organisms, all of it fits the profile of what you'd expect from a nearby supernova. And if it's true, it means that supernovae have not just influenced life on Earth, but have occasionally driven it to the brink. Now, here's a question that might make you pause. Could it happen again? Could a nearby supernova threaten Earth in the near future? The answer depends on what we mean by near future and nearby. Astronomers have identified several massive stars within a few hundred light years of Earth that are candidates for becoming supernovae. The most famous is Betelgeuse, a red supergiant in the constellation Orion, about 642 light years away. Betelgeuse is nearing the end of its life. Its core is likely filled with iron, and it could explode at any time, astronomically speaking. That might mean next year, or it might mean 100,000 years from now. We can't predict the exact timing. But when it does explode, it will be spectacular. It will likely become brighter than the full moon, visible during the day, casting shadows at night. It will remain visible for weeks, possibly months, before fading. And it will be completely harmless. At 642 light years, Betelgeuse is well outside the danger zone. We'll get a beautiful show, but no ozone depletion, no climate disruption, no extinction threat. There are other candidates closer to the danger zone, but none are immediate threats. The nearest known massive star that could become a supernova is Spica, about 250 light-years away. Still too far. The galaxy as large stars are spread out, and the probability of a supernova occurring within 30 light-years of Earth in the next million years is very low, perhaps less than 1%. We're in a relatively safe neighborhood, a quiet part of the galactic suburbs, far from the dense star-forming regions where supernovae are more common. That doesn't mean we're immune, but it does mean we're unlikely to experience a nearby supernova anytime soon. But let's explore the paradox at the heart of this discussion, because it's one of the most fascinating aspects of supernova and their relationship to life. On the one hand, supernovae create the elements necessary for life. Without them, there would be no carbon, no oxygen, no iron, no planets capable of supporting biology. On the other hand, supernovae can destroy life, stripping away ozone layers, bathing planets in radiation, triggering extinctions. They are both creators and destroyers, givers and takers. The universe doesn't care about balance. It simply does what physics allows, and sometimes that means a star explodes at just the right distance to seed a molecular cloud, with heavy elements leading to the formation of a solar system like ours. And sometimes it means a star explodes close enough to wipe out half the species on a planet. The universe is indifferent. It creates opportunities and threats with equal measure. This paradox extends to cosmic rays as well. We mentioned earlier that cosmic rays from supernovae constantly bombard Earth, causing mutations in DNA. Most of these mutations are harmful or neutral, but occasionally one leads to a beneficial adaptation, a new trait that helps an organism survive and reproduce. In this way, supernovae contribute to evolution. They're a source of genetic variation, a driver of change. Without cosmic rays, without the steady drizzle of high-energy particles from distant explosions, evolution might proceed more slowly, less creatively. Life would still evolve, but perhaps not as dynamically. So even the harmful effects of supernovae, the radiation, the mutations, have a silver lining. They push life to adapt, to diversify, to become more resilient. There's also a concept called the galactic habitable zone, the region of a galaxy where conditions are favorable for life, too close to the galactic center, and there are too many supernovae, too much radiation, too many close encounters with massive stars, too far from the center, and there aren't enough heavy elements to form rocky planets. The galactic habitable zone is the sweet spot, a ring-shaped region where supernovae are common enough to enrich the interstellar medium with heavy elements, but rare enough that they don't pose a constant threat to planetary life. Earth orbits a star in this zone about 26,000 light-years from the galactic center, in a region where the supernova rate is moderate, the heavy element abundance is sufficient, and the radiation environment is tolerable. We are once again in the right place at the right time. But here's something worth considering. If supernovae occasionally cause extinctions, they might also create opportunities. An extinction event clears ecological niches, allowing new species to emerge and diversify. The dinosaurs were wiped out 66 million years ago, likely by an asteroid impact. But the resulting extinction allowed mammals to flourish, eventually leading to humans. If a supernova caused the late Devonian extinction, killing off many marine species, it also opened up space for new forms of life to evolve. Trilobites, once dominant, declined. Fish diversified. The ancestors of land-dwelling vertebrates, including us, began their slow march out of the oceans. Destruction and creation intertwined, inseparable. There's a philosophical dimension to all of this that's hard to ignore. We exist because supernovae created the elements we're made of. We exist in spite of supernovae, which could have sterilized Earth if one had exploded too close. And we exist in part because supernovae drive evolution through cosmic rays and occasional extinction events. Our existence is tied to these explosions in ways both obvious and subtle, both beneficial and threatening. We are children of supernovae, and we are survivors of supernovae. both are true at the same time. Some scientists have proposed that the emergence of complex life on Earth might have been delayed or accelerated by nearby supernovae. If the supernova rate in our region of the galaxy was higher in the distant past, it might have kept the ozone layer weak, preventing complex multicellular organisms from colonizing land until the supernova rate decreased. Conversely, if cosmic rays from supernovae increase mutation rates, they might have sped up the evolution of certain traits. These are speculative ideas difficult to test, but they highlight how interconnected life and the cosmos really are. We don't evolve in isolation. We evolve within a galaxy that is actively shaping the conditions of our existence. And here's a sobering thought. Life on Earth has persisted for about 3.8 billion years through countless environmental changes, asteroid impacts, volcanic eruptions, ice ages, and, yes, likely several nearby supernovae. The fact that we're still here suggests either that we've been extraordinarily lucky or that life is more resilient than we give it credit for. Even a supernova within 30 light-years, while devastating, might not sterilize the planet completely. Microbes would survive buried underground or in deep oceans. Life would eventually recover, as it always has. The question is not whether life could survive a nearby supernova, but whether civilization could. Could human society withstand a decade of increased UV radiation, climate disruption, and agricultural collapse? That's a different question, and the answer is less certain. But let's also recognize the gift. Supernovae have given us more than just the elements in our bodies. They've given us a dynamic, evolving galaxy, a cosmos that changes and grows and creates new possibilities. Without supernovae, the universe would be static, simple, lifeless. Stars would burn out quietly, locking away their elements forever. Galaxies would be cold, dark graveyards of hydrogen and helium. There would be no planets, no chemistry, no complexity. The violence of supernovae is not just destructive, it's essential. It's the engine that drives the universe forward from simplicity to complexity, from emptiness to life. So, the connection between supernovae and life is not a simple one. It's not just that they provide elements or that they pose threats. It's that they shape the entire context in which life exists. They determine what elements are available, where those elements are distributed, how often radiation events occur, how quickly evolution proceeds, and where in the galaxy life can safely emerge. They are in a very real sense the sculptors of the living universe. And we are one of their creations. As we sit here under a sky filled with stars, some of which are dying, some of which will explode long after we're gone, it's worth remembering that we are part of this process. We are not observers standing outside the universe looking in. We are participants made of stardust, shaped by stellar deaths existing, because the universe is violent and creative in equal measure. And that connection, that deep entanglement between dying stars and living things, is one of the most profound truths we've discovered. But supernovae are not static relics of the past. They are ongoing phenomena, and our ability to study them has exploded in recent decades, no pun intended. New telescopes, new detectors, new techniques are revealing details about supernovae that scientists couldn't have imagined a generation ago. And those discoveries are changing how we understand not just supernova, but the universe itself. That's where we're heading now, into the modern era of supernova research, into the questions we're asking today, and the answers we're just beginning to find. On August 17, 2017, something extraordinary happened. For the first time in history, scientists detected gravitational waves in light from the same cosmic event. Two neutron stars, each about 1.4 times the mass of the Sun and roughly the size of a city, had been spiraling toward each other for millions of years, locked in a fatal dance. As they drew closer, they moved faster, orbiting hundreds of times per second in their final moments, warping space-time around them, sending ripples through the fabric of reality itself. And then they collided. The merger released more energy in a fraction of a second than the Sun will produce in its entire 10 billion year lifetime. Gravitational wave detectors on Earth felt the space-time ripple arrive. 2 seconds later, gamma-ray telescopes saw a flash of light. And over the following hours and days, telescopes across the entire electromagnetic spectrum turned toward the source, observing an event unlike anything humanity had ever witnessed. This was not a supernova, but something related to kilonova, and it opened a new chapter in how we study the deaths of stars. Before 2017, astronomy was primarily about light. We pointed telescopes at the sky and measured photons, particles of light arriving from distant objects. Radio waves, infrared, visible light, ultraviolet X-rays, gamma rays, all different frequencies of electromagnetic radiation, all carrying information about temperature, composition, motion, and distance. But light is only one messenger. There are others. Neutrinos, which we talked about earlier, barely interacting ghost particles that pass through matter almost unimpeded. Gravitational waves, ripples in space-time itself, predicted by Einstein in 1915, but not directly detected until 2015, and cosmic rays, high-energy particles that bombard Earth from all directions. Modern astronomy uses all of these messengers, combining them to build a more complete picture of the universe. This approach is called multi-messenger astronomy, and it's transforming how we study supernovae, neutrons, stars, black holes, and other extreme events. The story of gravitational wave detection is one of persistence and precision. Einstein's equations predicted that accelerating masses should produce ripples in space-time, but he thought they would be too weak to ever detect. And he was almost right. Gravitational waves are incredibly faint. When LIGO, the Laser Interferometer Gravitational Wave, Observatory detected the first gravitational waves from 2 colliding black holes. In September 2015, the signal stretched and compressed space by less than 1/10,000th the width of a proton. That's a distance smaller than an atomic nucleus measured across arms 4 kilometers long. The detectors had to be sensitive enough to distinguish this minuscule change from vibrations caused by passing trucks, earthquakes on the other side of the planet, even quantum fluctuations in the laser light itself. It took decades of engineering, billions of dollars, and the collaboration of thousands of scientists to make it work. And when it finally did, it was a revolution. LIGO has now detected dozens of gravitational wave events, most of them from merging black holes, but a few from neutron-star mergers. Each detection provides information that light alone cannot give. Gravitational waves tell us about the masses of the objects, how fast they were spinning, how they were oriented when they collided, and how much energy was released. Combined with light observations, which tell us about the temperature composition and expansion speed of the debris, we can reconstruct these events in extraordinary detail. The 2017 neutron-star merger, designated GW1-817, taught us more about neutron stars in a few days than decades of previous observations. Scientists confirmed that neutron star mergers produce heavy elements through the R process, the same rapid neutron capture process that occurs in supernovae. Spectroscopic analysis of the kilonova's light revealed signatures of gold, platinum, and other heavy elements. This single collision likely produced several Earth masses of gold, enough to account for a significant fraction of all the gold in the universe. But let's return to supernovae, because modern technology is revealing things about them that were invisible just a generation ago. One of the biggest mysteries in supernova physics is the explosion mechanism itself. We understand broadly that the core collapses, a shock wave forms, and the star explodes. But the details are fiendishly complex. Computer simulations of core collapse supernovae struggled for decades to produce explosions. The shock wave would form, then stall, unable to push through the dense layers above the core. It took years of refinement, incorporating neutrino physics, turbulence, magnetic fields, and three-dimensional effects. before simulations could reliably produce explosions that matched observations. Even now, with the most powerful supercomputers in the world, simulating a supernova from start to finish takes months of computation time and requires approximations and simplifications. The physics is just that difficult. One of the key insights from these simulations is that supernovae are not symmetric. The explosion is not a perfect sphere expanding uniformly in all directions. It's lumpy, chaotic, with plumes of hot material rising from the core cooler regions, sinking back, and turbulent eddies mixing everything together. This asymmetry is crucial to the explosion's success. If the shock wave were perfectly symmetric, it might not be able to push through the star's layers. But asymmetries create instabilities, and those instabilities help the shock wave break through. Observations support this. When astronomers measure the velocities of material in supernova remnants, they find that different parts are moving at different speeds, some faster, some slower, creating the filamentary structures we see in images. The universe is messy, and that messiness is essential. There's also a class of supernovae that has baffled scientists since they were first discovered in the early 2000s. Superluminous supernovae, or SLSNE, are explosions that are 10 to 100 times brighter than ordinary supernovae. They don't fit the standard models. They're too bright, they last too long, and some of them show unusual spectral features that suggest exotic mechanisms at work. One leading theory is that they are powered by magnetars neutron stars with magnetic fields trillions of times stronger than Earth's. If a magnetar forms during the core collapse and spins very rapidly hundreds of times per second, its magnetic field can inject enormous amounts of energy into the expanding debris, making it glow far brighter than expected. The magnetar acts like a generator, converting its rotational energy into light over weeks or months. Another theory suggests that superluminous supernova result from the interaction between the expanding debris and a dense shell of material ejected by the star before it exploded. Massive stars often shed their outer layers in the years or decades before they die, creating a circumstellar medium, a cloud of gas surrounding the star. When the supernova shock wave hits this material, it converts kinetic energy into heat and light, brightening the explosion. This is called a circumstellar interaction model, and it can explain some, but not all, superluminous supernovae. The truth is, we don't fully understand them yet. They're rare, perhaps 1 in 10,000 supernovae, which makes them difficult to study. But each new detection adds to the data set, and gradually patterns are emerging. Then there are the failed supernovae events where a massive star collapses but doesn't explode. Instead, the core falls inward past the neutron star stage and becomes a black hole, and the outer layers simply fall in after it. From the outside, the star appears to dim and vanish, swallowed by its own gravity. No explosion, no bright light, no supernova remnant. Just a star that was there one day and gone the next. These events are difficult to detect because there's no dramatic signal, but astronomers have found a few candidates. In 2009, a massive star in a nearby galaxy, designated N6946H1, brightened slightly, then faded and disappeared over the course of a few months. Follow-up observations confirmed that the star was gone, and in its place there was likely a black hole. This was evidence of a failed supernova, a core collapse that didn't produce an explosion. Scientists estimate that between 10% and 30% of massive stars might die this way, collapsing directly into black holes without a visible supernova. If true, it means we're missing a significant fraction of stellar deaths in our galaxy, hidden behind the event horizons of black holes. Modern surveys are changing how we find and study supernova. In the past, astronomers discovered supernovae by comparing images of the same patch of sky taken days or weeks apart, looking for new points of light. It was slow, labor-intensive work. Now, automated telescopes scan the entire sky every few nights using sophisticated algorithms to identify transient events. Anything that appears, brightens, or moves. Surveys like the Zwicky Transient Facility, or ZTF, operating at Palomar Observatory in California, discover hundreds of supernovae every year, along with thousands of other transient events like asteroid flybys, flaring stars, and gamma-ray bursts. The data is publicly available, and astronomers around the world analyze it, follow up on interesting events with larger telescopes, and publish results within weeks of discovery. In the coming years, even more powerful surveys will come online. The Vera C. Rubin Observatory in Chile, formerly known as LSST, the Large Synoptic Survey Telescope, will begin operations soon, and it will revolutionize transient astronomy. With its 8.4-meter mirror and massive camera, it will image the entire visible sky every few nights, detecting millions of transient events, including tens of thousands of supernovae. The sheer volume of data will be overwhelming, requiring machine learning algorithms and artificial intelligence to sift through the detections, classify them, and prioritize follow-up observations. Human astronomers won't be able to keep up. The era of big data astronomy is already here, and it's only going to accelerate. One of the goals of these surveys is to catch supernovae in the act, to observe them within hours of the explosion before the light has had time to fade or change. This is called shock breakout, the moment when the shock wave from the core collapse finally reaches the surface of the star and breaks free. It lasts only minutes to hours, and it's incredibly bright, especially in ultraviolet and X-rays. Most supernovae are discovered days or weeks after shock breakout, when they've already reached peak brightness, but a few have been caught early, and they provide valuable information about the structure of the progenitor, star the size of its radius, the density of its outer layers. Every early detection helps refine the models, helping scientists understand the diversity of supernovae and why some stars explode in certain ways, while others explode differently. There's also a growing interest in using supernovae to study dark energy, the mysterious force that's causing the expansion of the universe to accelerate. We mentioned earlier that Type Ia supernovae, the white dwarf explosions, are standard candles with known intrinsic brightness. By measuring how dim they appear from Earth, astronomers can calculate their distance, and by measuring their redshift, they can calculate how fast they're moving away from us due to the expansion of space. Plotting distance versus redshift for many supernovae creates a relationship called the Hubble diagram, and deviations from the expected line reveal how the expansion rate has changed over time. This is how dark energy was discovered in the late 1990s, and it's still one of the best ways to study it. Future surveys with thousands or tens of thousands of Type Ia supernovae, spanning billions of light years, will measure dark energy's properties with unprecedented precision, potentially revealing whether it's truly a cosmological constant, as Einstein proposed, or something more dynamic and exotic. But here's the uncomfortable truth that scientists are confronting. The more we learn about supernovae, the more we realize how much we don't know. Every new discovery raises new questions. Why are some supernovae so much brighter than others? What determines whether a collapsing core becomes a neutron star or a black hole? How do magnetic fields influence the explosion? Why do some massive stars lose their outer layers before exploding, while others don't? These are not simple questions, and the answers will require better observations, better simulations, and probably new physics we haven't discovered yet. There's also the tantalizing possibility of detecting a supernova in our own galaxy. The last one visible to the naked eye was Kepler's supernova in 1604, more than 400 years ago. Since then, we've built radio telescopes, X-ray satellites, neutrino detectors, gravitational wave observatories, and a global network of automated surveys. If a supernova occurred in the Milky Way today within a few thousand light years, we would detect it immediately, observe it across the entire electromagnetic spectrum, measure its neutrino burst, possibly even detect gravitational waves if the collapse is asymmetric enough. It would be a once-in-a-lifetime event, a treasure trove of data, and it would answer questions that have puzzled scientists for decades. Astronomers are waiting, hoping though they know the odds are low. Supernovae in our galaxy happen on average once or twice per century, and it's been more than 4 centuries since the last visible one. The universe doesn't operate on human timescales. One thing is certain: when the next galactic supernova occurs, we will be ready. Networks of professional and amateur astronomers around the world monitor the sky continuously. Satellites in orbit scan for gamma-ray bursts and X-ray flares. Neutrino detectors underground wait for the telltale burst of particles that arrives hours before the light. And when the signal comes, the entire astronomical community will mobilize, pointing every available instrument at the source, capturing data that will be analyzed for decades. It will be one of the defining scientific events of the century, a moment when humanity witnesses in real time the death of a star in our own galaxy, and understands for the first time every detail of what happens when gravity wins and a star tears itself apart. But beyond the science, beyond the data and the discoveries, there's something deeper here. Modern astronomy is revealing that the universe is not static, not predictable, not simple. It's dynamic, chaotic, full of surprises. Supernovae are just one example. Every year we find transient events we've never seen before, objects that don't fit any known category phenomena that challenge our understanding. The universe is still teaching us, still showing us new ways that matter and energy can behave under extreme conditions. And that sense of wonder, that recognition that we're only just beginning to understand the cosmos, is one of the most powerful motivations for continuing this work. So, where does all of this lead? What does it mean that we can now detect gravitational waves, measure neutrino bursts, observe supernovae within hours of explosion, and use them to map the expansion of the universe? It means we're living in a golden age of astronomy, a time when technology and curiosity have converged to give us access to phenomena our ancestors could only imagine. And it means that the story of supernovae, the story of dying stars, is not a closed chapter. It's an ongoing investigation, a mystery we're actively solving, piece by piece, one observation at a time. But as we stand here looking out at the universe with all these tools, all this knowledge, it's worth asking a final question. What does all of this mean for us? Not just as scientists or as curious observers, but as beings made of stardust, living on a planet formed from supernova debris, wondering about our place in a cosmos shaped by explosions we can barely comprehend. That's the question we're turning toward now. The meaning, the connection, the quiet realization that we are not separate from these dying stars, but intimately, inextricably linked to them. There's a photograph taken by the Hubble Space Telescope in 1995 that changed how many people think about the universe. Astronomers pointed the telescope at a tiny, seemingly empty patch of sky in the constellation Ursa Major, a region about the size of a grain of sand held at arm's length. They left the shutter open for 10 days, collecting every photon that drifted into the telescope's view. When they processed the image, they found not emptiness, but thousands of galaxies, each one containing billions of stars, each one billions of light years away. Some of those galaxies existed when the universe was young, less than 1 billion years old. And in those galaxies, stars were being born, living and dying. Supernovae were exploding, scattering heavy elements, seeding the next generation. The image, now called the Hubble Deep Field, was a reminder that the universe is vast beyond comprehension, old beyond measure, and filled with events we can barely imagine. And yet, here we are on a small planet orbiting an ordinary star, able to look at that image and understand what it means. That's the paradox at the heart of this entire journey. We are insignificant in cosmic terms, a brief flicker in a universe that will exist for trillions of years. And yet we are also significant because we are the part of the universe that has become aware of itself. We are atoms arranged in such a way that we can contemplate atoms. We are stardust that has learned to wonder about stars. Carl Sagan said it best, and his words are worth repeating. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. That's not poetry, that's literal truth. Every atom in your body was forged in a star or a supernova. The carbon in your DNA, the calcium in your bones, the iron in your blood, all of it came from explosions that happened billions of years ago, long before the Earth existed. You are not separate from the universe. You are the universe temporarily organized into a form that can think and feel and ask questions. And the questions we've been asking tonight, the questions about supernovae, about how stars die and what they leave behind, these are not abstract intellectual exercises. They're questions about us, about where we came from, about what we're made of, about whether we're alone. Because if supernovae create the elements necessary for life, and if those elements are scattered across the galaxy, mixing into clouds that form new stars and planets, then life might be common, or at least the conditions for life might be common. We don't yet know if we're the only planet in the universe where atoms have arranged themselves into something that can look up at the stars and wonder. But we do know that the raw materials are out there spread across countless star systems waiting. And that's a humbling, beautiful thought. Let's think about what we've covered on this journey. We started with the death of a star, with the moment when the iron core can no longer support itself and collapses in less than a second. We walk through the layers of a dying star, understanding how it builds complexity over millions of years, fusing hydrogen into helium, helium into carbon, into heavier elements until it reaches iron and can go no further. We felt the shockwave tear through the star's outer layers, carrying with it the energy of 100 billion suns compressed into a few weeks of light. We saw how that explosion creates the heaviest elements in the universe, gold and platinum and uranium, through processes so violent they can only occur in the most extreme conditions nature allows. We traced those elements as they scattered into space mixed with hydrogen and helium, and eventually coalesced into new stars, new planets, new chances for complexity. We stood in the aftermath, looking at supernova remnants like the Crab Nebula, still glowing nearly 1,000 years. After the explosion, powered by a pulsar spinning 30 times per second at its center. We learned about neutron stars objects so dense that a teaspoon of their material weighs as much as a mountain, and black holes regions of space-time, where gravity is so strong that nothing, not even light, can escape. We discovered that supernovae don't just create elements and scatter them. They also influence planets' atmospheres and life. They seed clouds with cosmic rays that drive evolution through mutations. They occasionally come close enough to strip away ozone layers, contributing to extinction events that reshape the tree of life. They are both creators and destroyers, givers of the building blocks of existence and occasional agents of catastrophe. And then we stepped into the present, into the era of multi-messenger astronomy, where we detect not just light, but gravitational waves, neutrinos, and cosmic rays, combining all of them to build a complete picture of how stars die. We learned that supernovae are still mysteries, that every new discovery raises new questions, that the universe is more complex and strange than we imagined. We saw that science is not a finished project, but an ongoing conversation between humans and the cosmos, a conversation that will continue long after we're gone. But here's what ties it all together, what makes this story more than just a collection of facts and observations. You are part of this story, not metaphorically, literally. The atoms in your body have been through this cycle multiple times. They were once in the core of a star, fusing together, releasing energy, building up layers of heavier and heavier elements. Then the star exploded, scattering those atoms across light years of space. They drifted through the galaxy for millions of years, eventually mixing with a cloud of gas and dust that collapsed under its own gravity, forming the sun and the planets. Some of those atoms ended up in rocks and water, in the primordial oceans where life first emerged. They passed through countless organisms, recycled over and over, until finally they became part of you. And someday when you die, Those atoms will return to the Earth, and eventually, billions of years from now, when the sun becomes a red giant and the Earth is either consumed or sterilized, those atoms will be scattered back into space. Maybe they'll end up in another star, another planet, another being capable of looking up and wondering. The cycle continues. Nothing is lost. Everything is transformed. There's a concept in Buddhism called interbeing, the idea that nothing exists in isolation, that everything is connected to everything else, that you cannot separate yourself from the world around you. Modern astrophysics has arrived at the same conclusion, but through a different path. You are not just connected to the world, you are connected to the universe. The light from distant stars touches your eyes. The elements in your body came from supernovae. The energy that powers your cells came ultimately from nuclear fusion in the sun, which traces back to the Big Bang. You are not a separate thing, observing the universe from the outside. You are the universe observing itself from the inside. And that brings us to a question worth sitting with. What responsibility comes with that knowledge? If we are the universe become aware, if we are the part of the cosmos that can understand its own history, its own structure, its own laws, then what are we supposed to do with that understanding? Some people find meaning in religion in the idea that there's a purpose, a plan, a reason for existence. Others find meaning in relationships, in creating, in leaving the world a little better than they found it. Science doesn't prescribe meaning. It can't tell you how to live or what to value, but it can tell you what you are, where you came from, and how you fit into the larger picture. And maybe that's enough. Maybe knowing that you are made of atoms forged in the hearts of dying stars, that you exist because the universe is capable of producing complexity, that you are a temporary arrangement of matter that can feel and think and wonder. Maybe that's a foundation on which to build a meaningful life. There's also something humbling in recognizing how much we still don't know. For all the progress we've made, for all the supernovae we've observed, and the equations we've written, and the simulations we've run there are still fundamental mysteries. We don't know exactly what happens at the center of a black hole. We don't fully understand what dark energy is, or why the expansion of the universe is accelerating. We don't know if there's other life in the universe, or if we're alone, or if consciousness is common or rare. We don't know if the laws of physics are the same everywhere, or if there are regions of the universe where different rules apply. The universe is vast, and we've only just begun to explore it. Every answer leads to new questions, and that's not a failure. That's the nature of discovery. There will always be more to learn, more to wonder about, more mysteries waiting at the edge of what we know. And perhaps that's the real gift of supernovae. Not just that they create the elements we're made of, but that they remind us of the scale and strangeness of the universe. A star, something that burns steadily for millions of years, can collapse and explode in less than a second, releasing more energy than it produced in its entire lifetime. That explosion can be seen from billions of light years away. The remnants can glow for thousands of years. The elements it scatters can eventually become planets, oceans, living things. And all of this happens according to laws we can write down, test, and verify. The universe is not random. It's not chaotic. It's structured, governed by physics, and we can understand it. That's extraordinary. That's miraculous in the secular sense of the word. We live in a universe that can be known, and we are the beings doing the knowing. So, what do we take from this? What do we carry with us when we step away from this quiet journey through the depths of stars? Maybe it's a sense of connection, a recognition that we are not isolated individuals, but threads in a cosmic tapestry woven over billions of years. Maybe it's a sense of wonder, an appreciation for the beauty and complexity that arises from simple laws operating over vast scales of space and time. Maybe it's a sense of responsibility, a recognition that we are the universe's way of understanding itself, and that understanding is fragile, dependent on minds that can think and tools that can observe. Or maybe it's just the simple, quiet realization that the atoms in your hand were once in the heart of a star, and that connection, that lineage is something worth honoring. Have you ever stood outside on a clear night, far from city lights, and just looked up? Not at your phone, not distracted, but really looked, letting your eyes adjust to the darkness until the Milky Way becomes visible, a river of stars stretching across the sky. If you have, you know the feeling. A mix of awe and insignificance, a sense that you're part of something so much larger than yourself that it's almost incomprehensible. And yet, you're still you, still here, still looking up. That feeling, that recognition of scale and connection is what science at its best can offer. Not certainty, not final answers, but a way of seeing the world that makes it richer, deeper, more worth experiencing. We've talked a lot about death tonight, about stars collapsing and exploding, about the end of things. But death in the universe is never really an end. It's a transformation. The star dies, but its atoms live on, becoming part of something new. The supernova fades, but the remnant persists, glowing, evolving, shaping the space around it. The cycle continues over and over across billions of years, across trillions of stars. And we are part of that cycle. We are not observers standing outside. We are participants made of the same stuff, following the same laws, connected to everything that came before and everything that will come after. So, as we close this journey, as the night deepens and the stars continue their slow rotation across the sky, let's hold on to that connection. Let's remember that the light we see from distant stars is ancient, that it traveled for years or centuries or millennia before reaching us, and that by the time it arrives, the star itself might be gone, transformed into something else. Let's remember that the elements in our bodies were forged in violence and scattered in explosions, and that this violence was necessary, that without it, we wouldn't exist. And let's remember that the universe is not a cold, indifferent void. It's a place where atoms can become stars, where stars can become supernovae, where supernovae can become planets, and where planets can become life. That's not indifference. That's creativity on the grandest scale imaginable. Thank you for being here, for listening, for drifting through this story with me. These journeys into the quiet corners of science, into the places where wonder and knowledge meet, are only meaningful because you're here to share them. If these stories bring you comfort, if they help you see the universe a little differently, then they've done what they're meant to do. And there are more stories waiting, more quiet nights to explore, more mysteries to unfold. The universe is vast, and we've only just begun. Sleep well, dream gently, and remember, you are made of light from stars that died before Earth was born. You are the universe looking at itself, wondering, and in that wondering, finding something beautiful. Good night.